Now we go to the board now. There you go. This is what we discussed yesterday. All right. What did we talk about? Aromatic molecules. I'm going to open the door a little bit. I don't think I need the fan. Aromatic molecules, the first molecule that turned out to be something special was Ch8-6.8.21.AromaticRules. Hi, Juan Carlos. Hi, Wolfgang. Hi, Blake. Everybody's coming in. So that compound had a formula, chemical formula that resembled same number of carbons with same number of hydrogens, Ch6H6, and so everybody kind of knew, all the chemists knew that it had degrees of unsaturation. What that means is, that means it definitely had double or triple bonds, maybe cyclic structure. You realize that when it's acyclic, the formula is CnH2n plus 2. If you put a double bond in that molecule, if this is the molecule, if there is a double bond, that means you're losing 2 hydrogens. Same thing happens when you cyclize it. When you cyclize a molecule, when you make a cyclic compound, like continuous cycle, right? Doesn't matter how many carbons are there. In order to connect the tail with the head, you need to lose 2 hydrogens too. So it's any cyclic compound or any alkene with 1 double bond is CnH2n, right? Then you lose 1 more then you lose 2 more hydrogens, make another double bond, then it becomes CnH2n minus 2, so on and so forth. Okay.
So I'm sorry. So to be cyclic, you're just an alkene?
Cyclic is not alkene, but the bottom line is that's a slightly different like mindset. So this guy, straight chain hexane, is C6H14, right? This one is C6H12. You lose 2 hydrogens because you need to make that bond, right? This is hexane. The ends are CH3 and CH3. Realize that every time you're trying to connect the dots, if you're trying to connect the dots, if this is CH3, let's use my hand. If this is CH3, let's say I am hexane, and these are the 2 ends of my body. One end has CH3 and another end has CH3. Now, if I'm trying to become a cyclic molecule, I need to make a bond between this carbon and this carbon, right? And in order for me to make a bond between my 2 carbons, I need to have a bond between the 2 carbons. So I have to lose this hydrogen and this hydrogen to free up those electrons to have a bond between my 2 end carbons. So when any straight chain molecule becomes cyclic, it loses 2 hydrogens and its formula becomes and its formula becomes 12, drops by 2 hydrogens from the original molecule. Same thing happens when you make an alkene out of that straight chain molecule. Again, you lose 2 hydrogens. It's all about losing 2 hydrogens, but they don't look the same, but they have same formula. This guy is also C6H12. That's all I'm saying. I'm just saying that when you see a molecule with a strange formula, right, this guy, when you do not have all the hydrogens that normally comes with a saturated straight chain molecule, okay, they knew that with the formula of 6 hydrogens and 6 carbons, that means either this molecule has whole bunch of double bonds or triple bonds, or has a cyclic structure, or has a combination of the two. Make sense, Natalie? So we talked about that, and I talked about the fact that in the beginning of like maybe 150 years ago, cracking the code of like the structure of Ch8-6.8.21 took chemists some time. It took them a long time. I believe several decades. I don't remember the history very well. It took a long time, and eventually Kekulé cracked the code. Kekulé had a dream of snakes biting their tail. I mean, and then eventually he saw something cyclic, and then he woke up and he realized that I think benzene is this particular molecule, Ch8-6.8.6, with weird behavior, is cyclic. And then eventually these rules came about that in order for a molecule to be aromatic, what is aromatic? Well, they have some smell and they have weird behavior. They have double bonds and they have a cyclic structure, but they don't react with bromine. They don't react with HCl or HBr like a normal double bond reacts. They don't add hydrogen gas like a normal double bond does. They don't react with any other similar reactions, similar reagents, the way a double bond like an alkene or alkyne do. So they knew there is something special about these molecules, and they said that's because of the aromatic stability. And then eventually they figured out that it's not only has to be a cyclic molecule, not only do they have to have alternate double bonds and a few other related rules which we'll discuss now, but they also have to have a specific number of electrons that can move around in that ring. Okay, we're going to discuss that. We're going to talk about some aromatic reactions, and then we're going to take a break and we're going to discuss stereochemistry. That's our plan today. Okay, so I'm just kind of going over where we left off yesterday. So we talked about that, and as I said, that this is a pretty dangerous molecule. It has a smell. It's a liquid. It boils at 70 some degrees. I don't remember exactly where it boils. It's a really nice solvent for doing a lot of reactions. I mean, when we organic chemists do a reaction to convert something into something else, we need a medium. The medium could be ethanol. The medium could be hexane. The medium could be benzene. Medium could be, it depends on what we are doing and what kind of reaction are we doing. So the medium has sometimes changes. Benzene is one of the very wanted media, okay? But unfortunately these days getting benzene is really a nightmare, okay? So then we talked about the rules. Basically, must have alternate double bonds. I also said that it means no sigma wall. We'll discuss it a little bit more. It should not have a sigma wall. However, it may have a carbocation, may have a carbanion, or may have lone pair or lone pairs. We will discuss that. You may be a little confused about what this entails. We'll discuss it. Then we talked about the Huckel's 4n+2 rule. That means the total number of movable non-stationary electrons should be written as 4n+2, where n cannot be a fraction. N has to be a whole number, including 0. Okay, we're going to practice that too. Then we talked about this molecule. It's not aromatic. This molecule, it's cyclic but not aromatic. This molecule, cyclic, has 2 double bonds but not aromatic because it's got some problem here. It's not alternate double bond. I said this is what I call sigma wall. Okay, what is labile electron? Then we looked at this particular molecule. It fits the bill, like number 1 and number 2 checks off. Cyclic, has alternate double bond, but then Huckel's pi electron rule, 4n+2 rule doesn't work, because the number of labile electrons is 2 + 2, 4. When you write 4 as 4n+2, n turns out to be half. That's bad news. That means n is not a whole integer. If n is not a whole integer, this is not aromatic. We will check, we'll go through some rules. Then I talked about what is labile electron. Labile electrons are pi bond electrons. It can be lone pair electrons. It can also be negative charge electrons. This is what we discussed yesterday. Let's continue. So I'm going to erase the board and write down the rules one more time on the right side, or maybe we will start analyzing some molecules. As we analyze, write down the rules while we analyze the molecule. Okay. Stare at the board. We take a look at the board for like 30 seconds. I'll see if I can keep my mouth shut. I'll just take a look at my phone. All right. I think 30 seconds have passed. Let's erase. Hopefully there is not going to be much drama with erasing. I need a new board. Let me complain. Some of you may have missed it yesterday. We were talking about doing a review on Thursday. What time did I say? I think 11. 11 to 1, something like that. Pre-final review. And we will also do a review on final day, 7 to 8. Or we just meet at, you guys just take the final at 8 o'clock. I don't know. It's up to you. If you want to sleep in a little bit more, that's fine too. And you don't have to come to that review. Maybe I'll just kind of like hang out, relax, and talk about some stuff regarding the final. Make it very informal so that you guys don't stress too much about that review. Yeah, so I'll make that Friday morning 7 to 8 like totally optional. I mean, any review is optional. You don't have to be there. Whenever I need the special cleaner to clean my board, that's actually a bad sign. Maybe it's a sign that I should do something different. Okay, so Chem 8, and I believe today is June 8th. June 8th. Aromatic, whatever, molecules, compounds. I'm just going to leave it there. Okay, so let's draw some molecules. Okay, let's see how much you remember. You can look at the picture from yesterday. Let's just check different molecules. All right. Is that molecule aromatic? Somebody say yes or no and then justify. Why not?
No, because I'm not alternating.
Okay. So Blake says it doesn't have alternating double bond because that means single double, single double, single double. Okay. So yes, absolutely. So it's not aromatic. And the reason is no alternating. I'm just going to shorthand it. No alternating double bond. That's perfect. You can also think about it as sigma wall. What do I mean by that? These are all sigma bonds. Sigma, 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 sigma. Now, this is what I call sigma wall. Now, why is that a problem? Okay, let me just tell you. Let me introduce another concept right now. I think this is pretty important in case you use it in the future. Maybe biochemistry 150. I think this knowledge is going to be valuable. Okay, why is this not aromatic, and why is this molecule aromatic? And why do we have to have alternating double bond? Okay, let's analyze that. This is benzene. Double bond here, a double bond here, and a double bond here. I'm just color coding it so that it's easier for everyone to see. And let's put this hydrogens like this stage color. Okay, this is benzene. Now, this particular molecule, benzene, checks off. I'm going to just use one color. Number one, cyclic. Number two, alternating double bonds or no sigma wall. Then I said carbon plus, carbon minus, or something with lone pair or lone pair. Okay. And then we said number of labile electrons should be equal to 4n plus 2, where n equal to 0, 1, 2, 3, etc., and not fraction. Okay. All right. So this particular molecule, Ch8-6.8.6, it checks off all those criteria. Yes, yes, we don't have to worry about that. And yes, because it's got 2 electrons here, 2 electrons here, and 2 electrons here. And this molecule is called benzene. This is called benzene. Now, why can we not have alternate double bonds? I mean, why can we not have sigma wall? What's the problem? And why does it have to be cyclic for a molecule to be aromatic? Well, here is the reason. Here is the real reason that I haven't talked about yet. Okay, the electrons that are in pi bond. If you can write down what is labile electron. Let's write that down in a different color. So labile electrons can be pi electrons. We talked about it yesterday, or lone pair, or negative charge. We will practice, so don't worry too much about it. Like if you're not completely following it, that's fine. Whenever you have continuous or alternate double bonds, like with these bonds that are kind of labile. So think about it this way. Think about these electrons as you know how double bonds happen, right? double bonds happen with one sigma bond, that's axial overlap, and one pi bond, that's side-to-side overlap, like two pz orbitals coming together parallelly and making a pi bond, right? That's how it happens. And I always told you that these laterally overlapped pi bonds are a little sketchy. They're kind of vulnerable. They're not the most stable ones. So how is this, how does this molecule look like when you are considering the three alternate double bonds? Okay, there is a, let me drop my pens. There is a 2pz orbital here. There is a 2pz orbital here. There is a 2pz, there is a 2pz. So each corner of the hexagon in benzene has a pole. Okay, think about them as a house with 6 poles around it, like a fence, and on top of each pole there is a monkey sitting there. Okay, this is my metaphor for aromatic molecules. Think about it that way. So this electron is sitting here on this pz orbital. This electron is sitting here on this pz orbital. This guy has that. So that electron belongs to carbon. Let's number it. Carbon 1, 2, 3, 4, 5, and 6. So this electron belongs to 6. This electron belongs to 1, etc. Right? So each pole has an electron, and at this time carbon 4 and carbon 5 are making a pi bond, right, between the poles. So these two are forming a pi bond. These two are forming a pi bond by side-to-side overlap, and so they are. Why do they have to make pi bonds that way? Why can't carbon 1 and carbon 2 make a pi bond? Who says that they cannot have a pi bond? Only 1 and 6 have to have a pi bond. So there is no such rule. So how does that happen? Well, if this is the situation, if the pi bonds were fixed forever, if only carbon 1 and carbon 6 were bonded with a double bond and this was always a single bond, how will benzene look like? Benzene wouldn't look like this. Benzene would look like something weird. Benzene would look like this. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Does it make sense to you? If the double bonds were stationary, okay, then the fence around the house would look weird, not symmetrical. Think about it for 15 seconds. Then I'll get back again. If the double bonds are fixed in space, this is how they would look like, because single bonds are longer, double bonds are shorter. And scientists, chemists could measure the bond lengths from long time ago. Even in the 20th century, 1900, mid 1900s, they could figure things out using some sort of spectroscopy and some other experiments. And this would be the case if the double bonds were stationary, right? This is expected at that time. Okay. In real life, again, it's just like you do your experiment and you find out if your expectation is correct or not, and then you come up with another rule. In real life, it turned out that's not the case. All the 6 bonds are identical. It's a perfect hexagon. Perfect hexagon. This is from experiment. And this is your expectation. Expectation turned out to be wrong, and your experiment says all the 6, C1 to C6, C6 to C5, C5 to C4, C4 to C3, and C3 to C2. They're all of equal length. So then came another concept. That's exactly how science forwards, right? So what does that entail? What does that new concept entail? Well, this is what it says, and that's where lies the secret of aromaticity. The bonds are not stationary. Okay, so this bond, the whole bond, like this is anchored here. So this electron, it can get unhinged from carbon 3 and can move in between 1 and 2, like this. This bond can move here. As it moves here, somebody has to move from here. So the blue bond moves away from carbon 1 and moves in between C6 and C5. And as it moves in between C6 and C5, the C5-C4 bond has to move here. They're basically, it's kind of like a musical chair. Think about 6 poles around a house, like part of a fence, like a hexagonal fence. On top of each fence, each pole, there is a monkey, and the monkey number 1 jumps to the pole number 2. As it jumps to pole number 2, the monkey on pole number 2 has to jump on pole number 3. And essentially, they're doing their monkey business by jumping one from the other, and it's like a continuous flow. So there's a monkey ring going on around the house, and when you have the right number of monkeys, your house is protected, and everybody's happy and safe and low energy, right? So as this happens, what does the molecule look like after they have shifted? Well, when it does that, let's see how the next stage looks like. Okay, these are the sigma bonds. This is the main frame of the hexagon. The hydrogens are not moving around. Hydrogens are still here. Now, let me just write down there. This is carbon 1, carbon 2, carbon 3, carbon 4, 5, and 6. I haven't changed them. One, like clockwise, starting from number 12. 12 is 1, and 1 is 2, etc., etc. Now, the blue bond is here. Okay. The red bond is here. And the green bond is here. Okay, this explains that sometimes the double bond is between here and here. Sometimes the double bond is between the carbons here and here. So all the carbon-carbon neighbors, the 2 adjacent neighbors, sometimes they're single bond, sometimes they're double bond. Make sense? Okay. So this process, does somebody know what this means when just the labile electrons are kind of like spinning around or moving around? They're not stationary, but no element is moving. No hydrogen is moving. No carbon is moving. You're not breaking a carbon-carbon bond. Nothing like that is happening. No bond breakage, no bond formation. All you are doing is moving the labile pi electrons. Do you know what that means? It's an R word, ends with an E, and you use that word for even in music when you have a string instrument. Anybody has any idea? RES. It's a long word. Something, when you say something is resonance. This process is called resonance. Okay, I'll tell you why it's called resonance. When resonance is happening, okay, this is the arrow that we show. We don't use a single-headed arrow, that's wrong. Okay, we don't use the equilibrium arrow, that's also not right. We use a double-headed arrow. Okay, resonance basically means Sometimes the double bond can be found here. Sometimes the double bond can be found here. Okay. Sometimes the double bond is here. 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 Okay. So sometimes this molecule is written as, you have seen it before, I can guarantee you have seen it. Sometimes we show it this way. The double bond is everywhere. And how do we show it? That's how we show it. Oftentimes, benzene is shown with a cycle. That means the monkeys are not sitting on their poles quietly. They are not localized. They are delocalized. High electrons are, this is an important word, delocalized. Delocalized means basically not stationary. Okay, so that's an important deal. Unless this delocalization happens, aromaticity doesn't happen. That's why it has to be cyclic. That's why it has to be alternating double bonds. And that's why there are some exceptional situations that can happen too. We'll talk about that in the next discussion. That's why it cannot be an acyclic like a hexane molecule with 3 double bonds. Okay, that doesn't work because there has to be a continuous flow of electrons, labile electrons, around that periphery of that molecule in order for that molecule to feel happy and stable and unreactive. Remember the 2 words that you need to connect: stable, unreactive. If I'm stable, I'm not going to react. If I'm unstable, it's very much, it goes hand in hand with this metaphor. It's like when you are happy and stable, you will probably talk less, unless you're me, and you will probably be less reactive. You will be unreactive. You will just want to be left alone and enjoy. When you are jittery, when you are unstable, you're probably going to react more easily. It's a perfect comparison between humanity, human behavior, and molecule behavior. Okay, it doesn't work all the time. So this is an important critical part. And the next critical part is the number of monkeys. If you have 6 monkeys, it's aromatic. If you have 4 monkeys in this molecule that we erased, if you have 4 monkeys, it doesn't work. Okay, it's not aromatic. 4 monkeys is bad number. 6 is a good number. Okay, physics involved. I can't claim that, I remember, but I don't want to explain it to you. But I don't remember exactly how this happens. You have to draw molecular orbitals in a cycle. You have to put the benzene ring in a certain way, and there is highest, you have filled molecular orbitals, unfilled molecular orbitals. If you ever learn that, I can probably help you at that point. I need to read up on that. It's kind of faded information. So this is what is going on in aromatic molecules, and this is why they become aromatic. In order for them to be aromatic, they need to spin around, and there has to be a right number of molecules. I think with this knowledge, when we analyze a few more examples, it'll make much more sense. So I contemplated whether I should talk about it because I was trying to save time, but I thought, you know what, whatever you learn in this course, you should learn it nicely and deep, properly, in the proper way. Then you can learn other things on your own. So whatever you're learning, if you learn it well, you might be able to pick up some other things when you are taking 150, and let's say I haven't covered it, you can still figure it out by flipping through the pages of the organic textbook. Take a look at the board for a few seconds. If you take a picture, and then we will analyze a few more molecules. I'm going to block the camera with my head. Okay, all right. This is number 1 picture.
I had a quick question just for
Yes.
clarification. So resonance means that pi bonds can alternate, and delocalize means that pi electrons are mobile.
Pi electrons are mobile. As the pi electrons are mobile, they're not stationary here. They're sometimes here, sometimes here. That's why we show an arrow, right? Sometimes this pi bond is here, sometimes the pi bond is here. Sometimes this pi bond is here, sometimes this pi bond is here. Essentially meaning that they are constantly spinning around. These electrons are spinning, like the 6 monkeys. Okay? They're constantly spinning around the periphery, around the edge of that border or the fence of the molecule. Okay? That's called delocalization. Why they're delocalized? Because they're not localized here. Sometimes this electron is here, sometimes this electron is here. Sometimes this electron is here, sometimes this electron is here. It can be here or here. 2 locations. If this is the post, the monkey can be here or monkey can be here. Sometimes here, sometimes here. So they're basically delocalized. So the bottom line is this delocalization process, as the electrons are moving around, that process is called resonance. I'll draw something, a musical instrument. It'll probably make a little more sense to you, how you can connect the dots. Natalie, did I answer your question or did I go around?
Yes. No, thank you.
Thank you. I don't know. Sometimes I think that I never answered the right way. Any other questions? You guys are following so far? Resonance might be useful when you, well, not as resonance, but you might be able to connect the dots when you're sitting in the biochemistry class. I think many of you are probably signed up for biochemistry in fall, right? Not sure. Okay. So what we discussed today, again, we kind of discussed the rules of aromaticity. Then I told you what's going on in these special molecules, and realize that resonance is not always happening in an aromatic compound. Resonance can happen in non-aromatic compound too. Resonance can happen in single bonded molecules as well, like acyclic compounds, like straight chain molecules. It can happen there as well. Maybe we'll do a few examples. So let's erase the board, and then let's analyze a few more molecules following the lesson that we just got. And I want to keep the chemistry of aromatic molecules to the minimum. It'll be a half-an-hour discussion. I'll just tell you that these are the 5 reactions. This is what happens. Just memorize it at this point. No point like going over the mechanism. I don't want to teach you any more mechanism at this point, unless I really feel compelled to do that. Okay, so let's check out few molecules. Let's check out the molecule that we had looked at yesterday. What was that molecule? Cyclopentane with 2 double bonds. Now you will appreciate what sigma wall means and why is it a bad thing for being an aromatic compound. Okay. I'm just going to use like some color for the double bonds. Okay, that's that. And this is the sigma wall. And now you will appreciate why I call it a sigma wall. These are all sigma bonds. Sigma bond means there is no pole with a monkey on that carbon. All the bonds are made by axial overlap and they're pretty darn stable. So these are all sigma bonds. So when you think about this entire molecule, if I numbered them, I don't know how am I going to number them. Let's say 1, 2, 3, 4, 5. carbon 1 has a p orbital with a monkey. There is a monkey here, there's a monkey here, there's a monkey here, there's nothing here, right? So remember, the monkey cannot jump a sigma wall. So this guy, they can mess around here, okay? If it pushes here, then this bond has to push on top of it. Let me just show you how resonance can still happen. It probably happens. So if I push this bond here, this bond has to move. Where is it going to move? There is no way it can move here. That's impossible. That's not possible because there is no one to take that electron. This is a sigma bond. This carbon has 4 electrons around itself. If this bond moves here, that's going to be violation of octet rule. That carbon, the blue carbon down here, carbon number 5, will have way too many electrons. That's not possible. That's forbidden. Okay, so this business cannot happen. So what can happen? Well, this bond can move on top of carbon 1. What will that look like? That will look kind of weird. So this is, let's say this bond has moved here, and those 2 electrons are now sitting here. Okay. Now, if I show you all the hydrogens, okay, you just deprived carbon 1, 2, 3, 4, 5. You just took away 1 electron from carbon 4 and you just dumped 2 electrons on carbon 1. Carbon 1 at this point has 1, 2, 3, 4, 5 electrons. Carbon is not supposed to have 5 electrons. Carbon is only supposed to have 4 electrons in its outermost shell. Now that carbon has an extra electron compared to a neutral carbon. Therefore, this carbon is negatively charged. This carbon 2 and carbon 3, they're okay. At some point, carbon 2 had a double bond this way. Now it has a double bond this way. So it's neutral. It's neutral. Carbon number 4 got screwed. It lost an electron. So this carbon is positively charged. This is also resonance. What just happened? You just moved the double bonds. Delocalization of labile or pi electrons. This is also resonance. This is legitimate resonance.
So where would the other double bond go? Or would it just be not double bond anymore?
The other double bond got split into a positive charge and a negative charge. This double bond, 3 and 4, moves between 2 and 3, creating a hole, creating a carbocation. So this end is a carbocation. C plus, because you took away that electron from carbon 1 and you added an extra electron to carbon, whatever, number 1. So this carbon is a carbanion. You created a carbanion, you created a carbocation, and you created a double bond. So that means it's a resonance situation, but I don't think the molecule likes this particular structure. So when you look at this molecule, cyclopentane with 2 double bonds, it may happen, but unlikely. The contribution to the real structure is probably going to be very, very nominal. It will be 0.001%. And that molecule will be, that structure will be 99.999%. Okay, this might be very little, but this can happen. There is evidence in different types of research work that this business can happen. But this business can happen keeping this area as such. Carbon 5 cannot take part in this monkey business because it's nothing but sigma. When you have when it's all sigma, it's like a huge mountain to scale. There is no way the monkeys can jump the fence. They cannot go past that. So in order for a molecule to be aromatic, that flow of electron has to be continuous. That's why you need alternate double bonds. Does it make sense? But this is legitimate resonance. Okay. So now this is not aromatic. Okay. This is not aromatic. For alternate double bond, blah, 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 all those reasons. Now, if you look at two other molecules, now I create a very similar compound, not exactly with a sigma wall, but with something interesting. I'm drawing the hydrogen so that you guys don't get lost. I'm going to just start with a carbanion, and I'm going to start with a carbocation. So I'm going to give this guy 2 extra electrons. Let's say that somehow it happens. So this guy, this particular molecule has 2 extra electrons. It's not a sigma wall. It's kind of a sigma wall, but not exactly. It's got a carbanion. And I told you that may be okay for a molecule to be aromatic. Now you will appreciate why it is okay to be aromatic. I'll show you. And this molecule will be bond deprived. That carbon number 5 at the bottom is bond with a positive charge. The whole, like nothing here. 1 electron is missing. It's supposed to have 4 electrons to be neutral. Unfortunately, somehow it lost that electron. It has a positive charge. Why they can be? Why there is a chance that either of this molecule can be aromatic? Because the monkeys can spin around the entire fence, entire periphery of that fence. How can that happen? Well, look how it can happen. We can have some legitimate resonance going on here. These 2 electrons can fall back in between these 2 carbons, pushing this bond to be a negative charge here. Resonance can happen. Delocalization can happen. Let me just draw it. What happens when the electrons are moving that way? Well, now you have a double bond here and here because you did touch this double bond, and now the electrons are sitting here, creating the negative charge here. It can happen one more time. This double bond can, the extra electron pair can move in between here and here, pushing this bond on top of that carbon. Okay? When that happens, it looks again different. This double bond hasn't been touched. Now there is a brand new double bond here, and the extra pair of electron has moved here. So if you number the carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So sometimes the negative charge is on carbon 4. Sometimes the negative charge is on carbon 2. Sometimes the negative charge is on carbon 5. So essentially what you're doing is you have some extra electron density. If you think about it like a honeycomb, not really a honeycomb, like a pentagon shaped, some kind of a honeycomb, right? Bees have made that. So, and there is honey around that 5 corners. but one of the 5 corners has excess honey. Sometimes that excess honey is here. Sometimes that excess honey is here. Sometimes that excess honey is here. Okay, but there is honey everywhere. Okay, the bottom line is those monkeys with one pole having an extra monkey, they're spinning around the periphery. Okay, so this is legitimate. When you have a situation like that, when resonance can happen along the periphery, it may be an aromatic molecule. What do you do at the very end? Well, you need to count. You need to still count the labile electrons. How do we count the labile electrons? Number of labile electrons is, how do we count it? What should be the number of labile electrons here? Anybody wants to pitch in?
6.
How do you get the number 6, Spencer?
From the
1,
2.
yeah, 2 and 2, 4. And so you're essentially counting these guys too.
Yes, the lone pairs.
2 plus 2 plus 2 equal to 6. We need to write 6 as 4n plus 2. We already know that it's going to be aromatic because we have seen it in benzene. So 4n equal to 6 minus 2, 4 equal to 4n. That means n equals 1, 4 by 4. N equals 1. Yes, it's aromatic.
So if it does that, it doesn't need the alternating bonds.
It's you don't need alternating bonds. In this case, you have an extra electron pair, and that's the bottom line is not alternating bonds. The bottom line is you need to figure out a way the electrons must be able to spin around the molecular periphery. That's the bottom line. It's not alternating double bond. So you can actually modify. That's why we have extra rules that carbocation may be okay, carbanion may be okay, something with a lone pair may be okay. Okay, so
What's kind of an example on how you would word this on like a final art quiz? Like, would you just ask if it's aromatic or is it? Would you make us find
don't
the
have to
direction?
really write down the rules. You will be seeing something, it'll make sense to you, or it will not make sense. So you will be able to figure it out. So alternating double bonds is rule number 1, but under that rule, you have sub rules, which is positive charge, negative charge, or lone pair may be okay. Maybe because what if the number doesn't count to 4n plus 2, n being a whole integer? It might not work. We'll check that out in a second. In like literally in like few seconds, we're going to see that in that molecule. That molecule looks like it can do resonance, but it's not aromatic. We'll see that in a second. Okay. So let's move and then we will discuss it again. Maybe Blake, if you still have questions, you can ask. Okay. So now this guy is a different kind of, it's going to do resonance, but in a slightly different way. How will it do it? Well, you've got electrons here. Remember, when you have no electrons, that's a hole. It's like there was a pole here. There is a pole. There is a hole in the ground. There is a pole sitting there with a monkey. There is a pole with a monkey. There is a pole with a monkey. There is a hole in the ground, but the pole is missing. Think about it that way. So if there is nothing there, nothing can flow from nothing, right? You cannot. So I know that this is not free response type of question. So this discussion is kind of meaningless, but I'm just trying to tell you the right from wrong, okay? You cannot show resonance this way. Electron cannot flow from nothing to something. Electron always flows from more to less. Make sense? So that's a wrong arrow. This is a wrong arrow. It always flows from rich to deficient center. Okay, so how will resonance happen here? The resonance arrows are going to look different from what we just did. This guy, this electron pair, just think about it this way. If this is a bond, it can unhinge from carbon 1 and it can connect to carbon number, whatever number is 1, 2, 3, 4, 5. Carbon 5. So 1 and 2 can unhinge and reconnect between 1 and 5. So let's number the carbons again. 1, 2, 3, 4, 5. Okay. So how can resonance happen? This way. That's your first arrow. That's the first resonance. That's how the electrons start moving. What does it look like after it happens? Again, resonance arrow, double-headed. One, 2, 3, 4, 5. 3 and 4 is untouched. Now there is a brand new double bond between 1 and 5. But when you did that, when you shifted that bond, you got carbon number 2 got screwed. Carbon number 2 has now the hole. You lifted that pole from carbon 2 and you shifted it to carbon 5. So now you got like little pothole, little opening on the ground over there. Can it happen one more time? Absolutely. What about the bond between 3 and 4? That guy can move. Between carbon 2 and carbon 3, again, another resonance structure can emerge. And now the double bond between 1 and 5 is untouched. And you have a brand new double bond between 2 and 3, and you shifted the hole. What does it mean? That means there is a hole somewhere, but the bottom line is the monkeys are spinning around with a hole. So it may be aromatic, we don't know. What's the last check we need to do? Count the number of labile electrons. What should be that number? Not Spencer, somebody else. Can you guys tell me what is the number of labile electron for this molecule? What should be the number of labile electrons in this carbocation?
Is it 24?
4, no.
4.
4, not 24. Only pi bonds, negative charge, lone pairs, they count. You don't count anything else. So how do we count it? There is a double bond here. Double bond means a sigma bond and a pi bond. Pi bond counts. How many electrons in a pi bond? 2. There is a second pi bond, 4. Nothing there. So then this number is 4. We already know from that molecule with like a box molecule, 4 doesn't work. 4 cannot be written as 4n plus 2 because n will turn out to be half. That doesn't work. So this is not aromatic. Make sense? Let's stop for a second.
I'm kind of confused on how the carb anion and the carbocation just like jump to the other side.
Okay. It's just electron movement. I'll show you one more time. Let's take a look at it and we will discuss that. I'll set up like a simple model system and I'll show you like how that happens. Just keeping things very simple. Okay. Okay. So the bottom line is maybe we can let's erase the board. I have 2 missions to accomplish right now. 1, answer Natalie's question, and number 2, practice a few more molecules. Let's answer Natalie's question first. Okay, so let's set up a very, very simple model system, like a pretty large one. Okay, 3 carbons. Okay, let's look at Let's look at a molecule that's the simple molecule with where electrons cannot flow. This is propane, right, Natalie? Natalie and everybody else. This is propane. Everything is sigma. Sigma means they are so tightly bound, they can't move around. Nothing can move around. So no resonance. Absolutely. No electron movement. Essentially saying no resonance. Okay, nothing. So done deal. Not negotiable. All right. So now let's say we have a molecule that looks like this. You already saw it before. Let's say there is a double bond. Okay, there is a double bond. Okay, there is a double bond, alkene. It has a double bond. It has a pi bond. So these are labile. I agree. These guys are labile. But where will they move into? In order for it to move, there has to be some assistance in the neighbor. If you let's say we dump it, let's say we force it to move. Let's say we do that. What will it look like? Check it out. We are doing something forbidden. Okay? If we do that, what will it look like? This carbon has 1, 2, 3 electrons. Now you're dumping that pi bond here. Okay? How many electrons does it have after combining? Over here, it's happy because it looks like a neon. Why does it look like a neon? Because it has access to a few more electrons. Right? After making bonds, it has access to 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. 8 electrons is what neon has. Therefore, the carbon is super happy. It feels like neon, right? So that's octet. This is what we say, octet is full. Your stomach is completely full, you're super happy. If you do this, how many electrons this carbon has access to right now?
10.
10, exactly. So it has access to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You cannot go beyond 8. It has to be 8 or less.
Right.
That's the octet rule. So this is forbidden. This would cause, this is just forbidden. This cannot happen. This is against the constitution of electrons. And of course, this guy got screwed, so it got a positive charge. So this cannot happen. You cannot flow into a sigma wall. This is a sigma wall. This is a sigma wall. Okay? So this guy cannot resonate. So no resonance. Now let's check out something where you can have resonance with this system. So no resonance because you have nothing labile. But let's check out another situation. What if we have a situation like this, but slightly different? We got 1 hydrogen here, 2 hydrogens here. We got a double bond here. That's kind of slanted. Should be the right angle, 120 degrees. And let's say over here, there is a hole. Somehow this guy lost an electron, lost a hydrogen, and created a hole. Can you have resonance here?
Mm-hmm.
How? Tell me, Natalie.
You can move the pi bond
Keep going.
to the left. Mm-hmm. And then I am gonna guess that the positive electron goes to the right, the other carbon.
Not positive electron, positive charge. There is no
Positive
electron.
charge, sorry, positive charge is gonna go to the right carbon.
Perfect. Mission accomplished. You got it. You know, I think it should make you feel good. It make you guys feel good. I usually don't teach resonance for Chem8, but I somehow got, you know, one thing led to another, and I got sucked into this discussion, and I'm enjoying it. Hopefully the feeling is somewhat mutual. I usually do not talk about it. So the double bond is now between carbon on the left and carbon in the middle, and the hole has shifted to the right. That sounds kind of weird, but then that's the way it is. So this is how resonance can happen. So if I have to draw this molecule with kind of showing like what's going on here, well, this is how I'm going to show it. I'll just put the double positive charge in the middle. So the positive charge could be here or could be here. It doesn't matter. That's how we show it. Let's do one more example. If you have a double bond, and instead of a positive charge, what if you have an extra electron density here? Can you also have resonance here? Anybody wants to help me out? It's a different scenario. Over here, there was a lack of electron. One electron was missing. Over here, I'm not showing the hydrogens, but we got two electrons as a lone pair, and carbon is kind of not supposed to have so many electrons. So it's negative. Can we do resonance here? And how do we move the electrons here? We cannot move it the way we moved over there. Electron moves from more to less. In this case, more and less is all relative. So in this case, the double bond is not the more guy. How do we move them? We take the extra electrons, move it between the left carbon and the middle carbon, and move the bond away. Follow the arrows and tell me if you're comfortable. Make sense? Natalie, everybody else?
What would it look like after that?
Hold on, you know what? Let me just spell it out. Okay. Okay with this so far?
Yes.
Two electrons here in the pi bond, that's a pi bond, side to side overlap, blah, 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 blah. Over there was nothing here. Somehow, this molecule lost a proton, but when the proton was plucked by a base, it left the electrons here. Therefore, this carbon is supposed to have 4 electrons, but now it has 5 electrons, therefore it is negative. Does it make more sense to you than the way I drew it earlier?
Yeah, I see it.
You see it now? Now, how can resonance happen? If it goes there and sits there, then this carbon will be kind of breaking the octet rule. Somebody has to go. Somebody has to move. Look at the arrows, everybody, and tell me if you're comfortable or not comfortable. resonance happens.
Mhm.
Carbon left, carbon middle, carbon right. Hydrogens have not moved at all. Hydrogens are pretty much where they are. Carbons are pretty much where they are. Now there is a double bond here between left
Mhm.
carbon and middle carbon. And
Mhm.
those two electrons are sitting on the end, on the right, making this guy negative. So it's resonance. So if I show it, in skeletal diagram, this is what it looks like. Basically, the negative charge is shifting around. If I have to show it in one color, I mean one form, how will I show it?
Dots. Negative. Got it.
Got it?
Makes much more sense. Thank you.
No problem, my pleasure. I'm glad that you are asking. Nobody usually bothers in Chem 8. I'm really impressed. This is definitely the best Chem 8 class I've ever had.
Me too. It's
What
the
do you
only
mean?
Chem 8 class I've had. It is great.
What do you mean, Natalie?
This is way better than general chemistry.
Of course, I told you so. Hey, Alejandra. Alejandra, where is the glow? Where is your glow? The angelic glow, like the heavenly glow. The glow is missing. Come on. I want the glow back. Okay, maybe take a 1 minute break. Too much resonance going on. I'll just draw something interesting. I mean, I cannot really, I mean, I can draw, I can copy, I can basically imitate, but when it comes to like drawing from my imagination, I suck at it. So essentially, the resonance basically means, where do I draw it? Right here, let's say. Let's say you have a musical instrument. I'm just going to draw some generic musical instrument that looks weird, but then you get the point. So let's say here are the strings. Okay, I'm just going to not draw this backside. Let's say there is a string here attached to this pole here through the bridge. I know what bridge means because our son plays viola. That's all I know. And then let's say it's connected to a pole here, right? Let's say that's the string. Okay. As you pull the string up, right? When you're playing it, you pull it. Where do you pull it? Let's say you pull it all the way to the top here. You pull it like that. Okay. Then you let it go, right? As you're pulling the string, as you're striking it, right? With whatever. As you let it go, okay, as you let it go, it goes past where it was. It goes past here, all the way to the other end. It's kind of like a parabola. It has the shape like that. It started out here, you pulled it up, you let it go, then it goes down, goes up, goes down. So it basically, it's vibrating, okay? So it's as it vibrates, what space does it cover? It's vibrating through this space, and eventually it's shrinking, right? Until it completely decays. We use the word resonance. The string is resonating. What does that mean? That means at any point, the string could be here, string could be here, string could be straight down here where it was, string could be down here, or string could be here. So that's what it means by the word a resonating string. Same deal here. That the extra negative charge is resonating. It could be here or it could be here. The positive charge is resonating. The positive charge could be here or here. The probability of finding the positive charge left or right is 50-50. So same deal here. The probability of finding the string at any point is going to be some probability. Okay, I'm not going to take a picture of that. Let's take like a minute break. We're going to go through some chemistry, another half an hour, and then 9 to 10:15. We're going to start talking about my favorite topic, stereochemistry, lefty and righty. Okay. All right. Let's. I'm not shutting down anything. I'm just going to sit here and watch something. I'm not going to tell you what I'm going to watch. If you guys want, you can talk, you can play, you can eat, whatever you want. 1 minute break. So 8:30. Let's say 8:30. It's 8:28 by my computer. We can have any chit chat on the side if you want. If anybody has had like really fantastic breakfast, you can tell me what you had. Like really fancy stuff. Oh, it's 8:30. How many of you have watched the movie called Back to the Future? Has anyone watched Back to the Future?
I
remember-
have.
You remember the car that was used? Do you know which car they used for Back to the Future? Do you know what it's called? It starts with a D. Do you remember what the car is called?
Oh goodness. I
Oh.
don't.
DeLorean.
DeLorean, right? So
Mhm.
there's an online place where you can basically there's always some kind of bidding going on for exotic, not necessarily exotic. Sometimes you can find like cheap stuff too. I'm going to just share it. It's called Bring Your Trailer. It's called BAT. I don't know if you guys know it. I'm just going to share it. It's very completely unrelated to Ch8 discussion. So you see there is a DeLorean on sale. The current bid is $48,300. That looks so gorgeous. I've never shared something like this with my students before. There must be something different about you guys.
You should buy it.
Yeah, exactly. I need to go and get some funding in the night, maybe after 9 o'clock. I need, okay, don't get me
Treat
fired.
yourself, professor. Treat yourself.
No, there is, you'll cry if I tell you how much money I make. You will have tears in your eyes. Seriously, professors don't make, it's true that the starting salary here, starting salary in a university like Fresno State, and hold on, I'm trying to get to my front camera. And Fresno State versus City College. City College actually pays their starting assistant professors more. I'm not kidding. That's true. So anyway, I'm not complaining. I like my job a lot. I'm not going to trade it for my industrial job where I could be making much more. So I'm not. Yeah, that environment sucks. Absolutely, a lot of lies and a lot of bad things that happen. I don't want to be part of that. Even though it's very challenging, even though there is a lot of failure, like getting grants and stuff, I would still take this job over. Peace is more important than happiness sometimes. All right. Okay. No more philosophical lecture. Okay. I'm going to shut up. I just got carried away looking at the DeLorean. Okay. Let's go. Let's go to the board. Okay. So let's erase the board. I took a picture. I think I did. Let's quickly spend a few more moments, maybe 15 minutes on a few more examples. Okay. I'm not going to be OCD about cleaning my board right now. Let's get moving. Okay. I'll let it go. It's not easy because those specks and the lines, they bother me, but I'm going to let it go this time. Okay, so aromatic, we don't have to dwell on it anymore. Cyclic, alternate double bonds, 6 electrons can be written as 4n plus 2. We already covered it. Cyclic, alternating double bonds, yes, yes. Number of electrons, 4. Nope. Nope, cannot flow around. 4 electrons, bad idea. We talked about double bond, double bond, double bond. Well, right number of electrons, labile electrons, but there is a problem here. Nope, cannot flow through. Alternate double bonds are not there. This guy, well, yeah, it can flow around, so that may be aromatic. Number of electrons, 4. Nope. Two plus 2 plus 2, 6. Yes. Aromatic. Now let's introduce something else. What is your gut feeling? This molecule, it's called pyrrole. Pyrrole is in a molecule, a protein called porphyrin. It's involved in catching oxygen and delivering it in your body. Okay, it's fascinating. You will learn it in 150. And it's there are 4 pyrroles. All the nitrogens are in the center. There is a metal bound in between the 4 nitrogens, and that metal catches the oxygen, and the oxidation state changes. It releases the oxygen. It's fascinating. Biological chemistry is where chemistry and biology can marry and work together and fulfill each other's deficiencies and do really magical stuff. It's awesome. So this molecule is very, very special in evolution, in human beings, in any living creature. So this pyrrole, tell me, aromatic or not aromatic? What do you think?
Not aromatic.
Oh, Spencer, you hurt my feelings.
I think it is aromatic.
Once our colleague, he was a chair, he was my old friend, Saeed, he's the director of Smith Camp. His daughter said, she was really, really little, she said, I hurt my feelings in this morning. Since I've been saying that, I hurt my feelings. Okay, Natalie thinks yes, Spencer thinks no. How are you going to divide this empire with a yes and no people? Which one is correct? Anybody else? You guys shut up. Somebody else. Who wants to take side with Spencer? Who wants to take side with Natalie? Anybody? Or are you going to play the political game like, I don't know, Dr. Mitra? Okay, I have 2 other cameras on, Josie and Alejandra. Which side do you want to take? Count the electrons, people. 1, 2, 3, 4. Is that it? Can somebody do the monkey business here? That doesn't look like an usual suspect, but a little unusual suspect.
There's 6 because of the lone pair.
Yes, Josie. They can do monkey business.
It'd be no, wouldn't it be?
No, yes, Blake. Because the lone pair can participate in the monkey business. They can spin around, they can resonate. You can think about it like this. I'm not going to show another one. I'm not going to elaborate on it. So the lone pair can drop here pushing the bond here, pushing a negative charge here, then the negative charge can push back down here, the bond can move here. So yeah, it's going to be kind of ugly. Like everybody wants to be neutral. Nobody wants to be like charge separated. But the nitrogen, it will become positive. Let's show it.
Isn't it still a sigma bond though? Around the end?
Oh, hold on. So yeah, sigma bond. Yeah, I know what's bothering you. Okay, yeah, sigma bond. That's perfect. I'm proud of you guys. That's the lone pair. That's the hydrogen. There is a pi bond here. There is a pi bond here. Okay. Now, in order for a pi bond to happen, I told you guys that they have to be perfectly parallel. Parallel, 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 and parallel. This bond, the lone pair, this is sigma. You are absolutely right. This is sigma, this is sigma, this is sigma. This is also sitting in a sigma bond. You caught that very well. Okay, it's at an angle 109.5 degrees. But even though this is sp3, and even though all these four guys are sp2, again, it's not someone's dream. It's evidence-based. Okay, it has been found that this molecule pyrrole has aromatic character from other resources. Therefore, the chemists go back and say, how do I explain it? Well, resonance is happening. Monkey business is going on in the periphery of the house. So what happens is it shifts its hybridization, and it does the monkey business. The lone pair, even though it is at an angle, even though it is not perfectly perpendicular, but it does become perpendicular, the nitrogen goes to sp2 hybridization. What happens here? It gets pushed down here. This pi bond gets pushed up here, and it does resonance. So if you ask my wife, what's the hybridization of the nitrogen in pyrrole, she will never say sp3. She will always say it's sp2, and she's correct. I'm kind of wrong. But when you are starting to imagine this molecule, I still like to tell you guys that it's in sp3 hybridization. Okay, I don't know what's right. If I'm right or she's right. Okay. The lone pair is now here. This is the lone pair. This nitrogen at this point had a happy situation. 1, 2, 3, 4, 5 electrons within its control, and it was neutral. At this time, it lost its lone pair between the next door carbon. And this pi bond is still intact, nothing has gone wrong. This pi bond, which used to be here, had got pushed up here. That means this carbon is negatively charged and the nitrogen got screwed. Nitrogen is positively charged. Nitrogen is supposed to have a nice unmessed with lone pair. That lone pair is gone. Now it's supposed to have 5 electrons. It's got only 4 in its valence shell. 1, 2, half of this bond, 2, half of these 2 bonds, 4. Therefore, it's positive. Okay, and this is a resonance contributor structure. And what does the hybridization look like? When you have all sigma bonds, it's sp3. When you have a double bond, it's not sp3, it's sp2. So it just switched to sp2. It's sp2 hybridization. This guy is not in sp2 hybridization. This guy has become sp3. The resonance can happen one more time. This negative charge can push down here. This bond can push up here. I'm just going to draw this molecule in one shot. One color, sorry. Oops, wrong bond. Here and negative charge here. So the monkey business is happening. In pyrrole, some weird monkey business is going on, including the lone pair. The lone pair is involved in this business. And how do we count the number of electrons? Whoever is doing the monkey business. Who is doing monkey business? These two electrons, and these two electrons. So the number of labile electrons that are getting delocalized is not 4, is 6. That includes the 2 electrons in the lone pair. 6 is a right number. We already know that. 4n plus 2, n equal to 1. Aromatic. Let's do one more. What if we have a situation like this? How do we deal with it? Well, it's almost like benzene, but not benzene. This molecule is called pyridine. It's another natural molecule. It stinks, and it's actually toxic. It has effect on the reproductive system. Pyridine is not good. Okay, pyridine. Do you guys think it's aromatic or not aromatic? What do you guys think? What's your gut feeling? Follow your gut feeling. Listen to your heart. Don't listen to your brain, because your
It
brain
is aromatic.
Sorry, Juan Carlos.
It is aromatic.
Okay. You want to explain why cyclic, alternate double bond, and number of electrons, Juan Carlos?
It is 1, 2, 3.
4, 6. Do we count the lone pair? Yes or no?
I want to say no. Yeah, you don't.
You don't. Okay. So you're saying it's 2 plus 2 plus 2 equals
Yeah, 6.
6. And you're saying it's aromatic. And you're saying we don't count. And you're right. But I want someone to kind of come up with a rule so that you can easily say, this is the lone pair that I'm going to count. This is the lone pair that I'm not going to count. I'm going to draw this molecule one more time down here and tell me how should we not screw up the exam. This is a lone pair. He's saying, don't count. And this is a lone pair that we came to realize that we should count. Come up with a rule, like how should you remember which one to count and which one not to count?
Is it because it doesn't have a charge on it?
Nobody has a charge on it, but one is supposed to be counted and one is not supposed to be counted. What's the difference between the two nitrogens the way it's written? Think about the go ahead.
Because there's a double bond next to the nitrogen on the left one.
Talk about hybridization, Spencer. So yes, this is in one kind of hybridization. This guy is in different kind of hybridization. What hybridization is this guy in? The way it's drawn.
sp2.
Think again, correct yourself.
Sorry, sp3. Sorry, you're on the right. Yeah.
Yeah, on the right is sp3. On the left is sp2. If it is sp2, don't count. If it is sp3, count. Remember it for tomorrow and for Friday. There will be some questions that'll be necessary. Another rule that I'm going to simplify it and keep it very simple. Okay. You can also have another molecule where you can have two lone pairs. How do we go about it? Is this, what do you guys think? Listen to your heart. Don't listen to your brain. Use your gut feeling. Use the force. This molecule is called furan. F-U-R-A-N. Do you think furan is aromatic or not aromatic? What's your gut feeling?
It's not.
Okay, Spencer says not. Should we cheer or jeer? Should we boo or what's the opposite of boo? I don't know. English is not my first language. If there are two lone pairs, how many lone pairs should you count when you're counting? How many monkeys can participate in the monkey business, jumping from one pole to another? Imagine like there are 4 poles with 1 monkeys, and there is 1 pole that looks like a slingshot. There is a monkey here, there is a monkey here. Can both monkeys participate, or only 1 monkey will participate? Sometimes this guy, sometimes this guy. What do you think? Use this monkey business metaphor, and it really works here. Now we'll be having nightmares about monkeys tonight. So you have 4 poles around the house. Pole 1, pole 2, pole 3, pole 4. Each has a monkey. 5th pole is weird because your grandfather, when he was setting up the fence, he could find one and he was too lazy to cut it into like a single pole. He said, it's going to look like slanted. I found this stake from the garden, from a tree that looks like a slingshot, and I just used it. It kind of looks cool. None of our neighbors has that kind of fence. And so now there are 2 monkeys sitting here. Only 1 can participate. So if that makes sense, when they're doing jumping from one pole to another, one monkey has to take its turn, right? So you just count 1 lone pair. If you count 1 lone pair, so you count that, and this. Don't count that. So then it's aromatic or not? What do you guys think?
It is aromatic.
Yes. Let's take a 2-minute break. It's 8:51. I'm going to stop. Oh my God, did I start recording? Yes, I did. I'm going to stop recording. Somebody should remind me when we get back. Let's get together in 8:54. Just 2 minutes. I'm not shutting anything down. I'm just going to stop recording for a few seconds. We'll talk about reactions of aromatic molecules. All right, I'm going to sit down here for a few minutes. We're going to meet like very soon.